Good morning to all of you. Now we are discussing about these properties of pure substances for last few classes, phase diagram. So today we will be closing that topic by discussing one aspect of this, which is known as Clausius-Clapeyron equation. Now we have recognized that saturation states are specified by the couple of pressures and temperatures, both for transformation from liquid to vapor and so from solid to liquid. Now what is the relationship between these two, so that if one knows the pressure, he can automatically know the temperature, based on which the pressures and temperatures are determined and tabulated. For an example, in steam tables. For water, we know that when saturation pressure is fixed, temperature we know. For example, if it is 1 atmospheric pressure, then the saturation temperature is 100 degrees Celsius. Similarly, the pressure is 10 atmospheric, what is the saturation temperature? So what is that relationship based on which the values are tabulated was given by two scientists, Clausius and Clapeyron. So this we will discuss today. Now let us again recall the PV diagram. Let us again recall the PV diagram. This is the PV diagram, this is the P and V as usual. We are bothered only on the liquid vapor, doesn't matter, we can consider this for solid liquid also. Similar thing will apply, and this is the TS diagram. This is the TS, I am drawing it like this. So this is liquid, liquid plus vapor. So this is the triple point line, solid, vapor, solid, vapor. Now here we see that if we denote the pressure, for example, at a given pressure, this is the constant pressure line. So this is the pressure, the saturation temperature for this pressure is the isotherm which passes through this, coincides with this pressure line in the vapor dome. As we know, this is the isotherm. That means if this be the pressure, the corresponding temperature is this isotherm. Similarly, here also, if this be the isotherm, let this be the isotherm T. What is the pressure? Corresponding pressure is this one. So corresponding pressure is this one. This is P. That means P and T here represents the saturation pressure and temperature. Well, now what are the relationship between this P and T? That means if we increase the pressure, the temperature will increase. Now let us recognize one thing, that you see in this type of phase change, what happens, the specific volume changes as this change of phase takes place. The specific entropy changes. Similarly, the specific enthalpy changes, which is found in HS diagram. But now if we define the Gibbs function, specific Gibbs function, according to its definition, G is equal to, what is the definition? H minus Ts. Now if you differentiate this, dg is dH minus Tds minus S dt. What is dH minus Tds? Is P VdP, I am sorry, VdP minus S dt. This relationship we also deduced earlier. So specific Gibbs function, that is why it is small v, specific volume, small a, specific entropy. Now you see, during this phase change, since pressure and temperature remains constant, which means dP and dt 0, so therefore dCg. That means we see another thermodynamic property, that is the Gibbs function, not the specific Gibbs function, that remains constant along with pressure and temperature during a phase change of phase from one state of matter to other state of matter. This is one very important conclusion. Now if this is so, then we can tell that this Gibbs function here, if we denote it as Gibbs function of the liquid and if we denote it as Gibbs function of the vapor, since we are using G, we are not using F and G, otherwise it will be confused. For all properties we have seen, even in the steam table, the subscript F is used for the liquid and subscript G is used for this trisaturated vapor. But here we are using G itself as the specific Gibbs function. I am using superscript L for the liquid and that for the vapor. So from this relationship we can tell that at a particular pressure and the corresponding temperature, this G of L, that means of liquid state, is equal to G of V, that is that vapor state. Clear? Now we consider a small, infinite small change in temperature. To find a relation, we have to do like that, an infinite small change in temperature or pressure, whatever you call. Here you see the pressure first. That means if this is P, all the time this change of pen. So this is P, so this is P plus dP. Similarly, the isotherm which passes through this, that means the saturation temperature, this suffers also a small change, that means T plus dt. That means here this is T plus dt. If this is T, this will be T plus dt. And similarly, the isobar which passes through this coincides with this constant pressure thing, that means this isobar is P plus dP. That means we change the pressure from P plus dP. We want to see what is the corresponding change in the temperature. Let this is T plus dt. And for this, let us consider that the Gibbs function in the liquid phase as a change from GL to GL plus DGL, and the vapor phase Gibbs function changes from this to GV plus DGV. Again they are equal because at this point this G and this G, that means Gibbs function for the saturated liquid and disaturated vapor are equal. That means these two are equal. That means one can write therefore DGL, which simply means that change in the Gibbs function for the liquid state will be same as that for the vapor state, so that they again become equal if the states are saturation states. So how to write then? Okay, you keep this, please. Sorry, you keep this. Okay. Okay, all right. Okay. So therefore, what we get, DGL is DGV. Now if we write this expression, DGL is V dPL or dP, dP is the same, minus VL minus SL dt is equal to what we can write for this following this equation, VV dP minus SV dt. This dP dt is not 0. This dP dt indicates a change in pressure and temperature like this. There is a change in pressure and temperature for which there is a change in the liquid phase Gibbs function, which must follow this general thermodynamic relation. That means dG is V dP minus S dt. Whenever there is a change in pressure and temperature, there will be a change in Gibbs function. Okay. So therefore dG is this and dGV is this. This is clear? From which we get dP by dt is equal to what? dP by dt will be equal to, then we can write SV minus SL divided by VB minus VL. Well, this SV minus SL is what? That is the change in the entropy, specific entropy for change of phase, which can be written as your latent heat divided by the saturation temperature into VB minus VL. Sometimes the latent heat may be written in terms of the enthalpy change HFG. Sometimes it is neither by L or by HFG, and this is one of the very important property relations. Okay? This is one of the very important property relations. Well, this is one of the very important property relations. Sorry, not property relations, I am extremely sorry. This is one of the very important relations, not property relations, I am sorry. dP dt, that is the change in pressure with respect to temperature, is L by T VV minus VL. Again I write this expression, therefore what we get is that dP dt is equal to L or HFG divided by T, that is the change in the specific entropy. So this equation is known as Clausius, these two scientists, Clapeyron equation. So therefore this equation gives the relationship between the saturation pressure and the saturation temperature. Well, that means from this differential equation we can integrate, but integration is not very easy. This is because of the fact this Vb is a function of temperature. Usually Vl is very small with respect to Vb. Sometimes we can neglect this because the specific volume of the liquid is very small compared to that of the dry saturated vapor. So HFG is also a function of temperature. So until and unless we know the functional relationship of HFG Vb with temperature or pressure, we cannot integrate it. So therefore this equation can be integrated provided we know this variation. Usually these variations are given in terms of empirical equations so that one can integrate this equation and express an explicit functional relationship of P with respect to temperature. That means this is the relationship of the saturation pressure corresponding to the saturation temperature. This pressure is sometimes known as vapor pressure. So vapor pressure versus temperature relation. Sometimes we tell colloquially that what is the vapor pressure temperature relations, means what is the relationship between the saturation pressure to its corresponding saturation temperatures at which a phase change takes place. Now you see here, in case of liquid vapor transitions, Vb is always higher than Vl, HFG is a positive quantity, T is a positive quantity, dPdt is positive. That means pressure changes with the change with the temperature. In case of solid liquid transitions, that means melting or freezing, so it will be, in case of solid liquid, this equation can be written as HFS, that means SF, that means I can write latent heat for melting, latent heat for melting. Usually this nomenclature is used, and in that case Vf, Vb will be Vl, that is the final phase, minus this is the initial phase, that means Vs. Now this will be positive provided on melting the specific volume increases. So for the substances where melting increases the specific volume, that means the system expands on melting, dPdt is positive, means an increase in pressure will increase the saturation temperature. For substances where Vl is less than Vs, that means the system contracts on melting, in that case dPdt is negative. That means an increase in pressure will reduce the saturation temperature. What happens in case of water? Clear? Okay. All right. So in this case dPdt is negative, and when Vl is greater than Vs, dPdt is positive. So this is the case for water in case of solid liquid. Just I give this example, but we are not much bothered on this aspect. We are only concerned with the boiling. That means when the vapor is transformed into liquid. So this is so small, sometimes it can be written as HFG T Vb. For all liquids, Vb is much higher than the Vl. Clear? Very simple. Now I come to the very simple, old and known things to you, ideal gases. This will be mostly the recapitulation of the things which you have read at your school levels with addition of few materials, but brushing up your concept. Now you see, for any compressible system, a functional relationship between pressure, volume and temperature, these three fundamental properties of a system. As you know, pressure, volume and temperature, all these three are directly measurable and sensible also. We can sense pressure and temperature. So this, a functional relationship between these three properties is known as, what is known as what? Pressure, volume and temperature is known as equation of state. Equation of state. This is known as equation of state. Now an ideal gas, if we ask what is the definition of an ideal gas, it can be defined in various ways. You can start with, but all the definitions are same, one is a corollary of the other. So you can start from the equation of state point of view. An ideal gas is a gas which obeys this relationship as the equation of state at all pressure, volume and temperatures. At any state points, the relationship will be PV is equal to mRT, where m is the mass of the gas, m is the mass of the gas, and R is a constant known as characteristic gas constant, whose value is constant for a particular gas but varies from gas to gas. So this relationship, this very simple relationship has to be valid at all state points. It has been found in practice that all the gases in reality do not exactly obey this equation, this functional relationship between PV and T. Gases only obey with a fair accuracy this relationship when its pressure is extremely low, P tends to 0, very low, or temperature is extremely high. I will not write infinity, this will odd, because at very high temperature the gases are ionized and is converted into another state known as plasma state, which is not a neutral state, ionized state. So at very high temperature, which means if the gases are highly superheated or rarefied, for example, we consider air. Air is at a tremendous superheated condition or a rarefied condition. I expressed this thing earlier while discussing the phase diagram. What is a superheated or rarefied state? Air is a superheated state, is a high degree of superheat, because if we consider air at the atmospheric pressure, then if we think its temperature, for example, today just now I have been told that temperature is 23 degrees Celsius. But what is the temperature at which air condensed or liquid air boils up at 1 atmospheric pressure? Though liquid air is not a pure component, it consists of nitrogen, oxygen, but their boiling points are very close. So we can take a rough idea that it is some minus 170 degrees Celsius or so, approximately. So you see how much degree of superheat it is. That means it is at a highly superheated condition corresponding to its existing pressure. At the same time, if you consider that 23 degrees Celsius as the existing temperature at which air can be liquefied, yes, it can be liquefied if you compress the air. And to do that, you will have to compress the air up to 50 or 100 atmospheric pressure or even more, so that air is at a rarefied state. So therefore, a very, very superheated or rarefied state, a gas obeys. That means when the pressure is very low and temperature is very high, obey this equation of state. Okay? This is experiments. But theoreticians on the other hand have derived this equation from kinetic theory of matters, provided they are allowed to assume certain postulates. That means they have to make certain assumptions. What are those assumptions? Number one assumption is that the molecules are, I am not writing all these things, it is boring, molecules are point masses. That means molecules are point masses, they do not have any volume. The volume of the molecules are neglected in comparison to the volume of the geometrical system. That is number one. Number two is that no cohesive force. What is cohesive force? Cohesive force is the force of attraction or repulsion between the molecules of the same kind. In fluid mechanics, you have learned that there are two types of forces, intermolecular forces, they exist. One is the force of cohesion, which is the intermolecular forces, forces of attraction and repulsion in between the molecules of the same kind. That means for a given system which comprises a large number of molecules, there are internal forces, attraction and repulsion forces of the molecules, which largely depend upon the molecular density. That means mean free path of the molecule, the distance between the two molecules. The mean free path, how do you define? Statistical average of the distance between two successive collisions. So therefore, these intermolecular forces are known as cohesive force. Another force is the adhesive force, force of adhesion, which is the intermolecular forces between the molecules of the two different kinds, between two different systems. So the molecular cohesive forces or molecular attractive or repulsive forces are zero, and because of which molecules are capable of moving in a straight line, rectilinear motions. So if you assume these things, then from the kinetic theory of matter, one can derive this relationship PV is equal to mRT, and the kinetic energy of the molecule is a function of temperature only, which gives the concept of temperature from statistical thermodynamics, which was given by Maxwell and Boltzmann. So this is beyond the scope of this classical thermodynamics which we are dealing with now. So if we know these informations, that is sufficient that an ideal gas from kinetic theory of matter have these assumptions that the molecules do not have any volume, and the internal forces between the molecules, that the cohesive forces in molecules are absent and molecule moves perfectly in a straight line, rectilinear motion, one can deduce this. But we are not much bothered of these assumptions in the kinetic theory, we are only bothered in classical thermodynamics with this equation PV is equal to mRT. Now Avogadro gave an hypothesis after this. Now you see PV is equal to mRT. Now we know from Avogadro's hypothesis, after the Avogadro hypothesis was discovered, there is another way of expressing the mass of a substance. This is the m whose unit is kg in SI unit. But another way of expressing the amount of a substance as a fraction of its molecular weight. That means if I defined n as a fraction of the molecular weight of the system, that means not in terms of its actual mass in kg, but in terms of fraction. For example, if there is 32 kg of oxygen, so its n will be 1 because the molecular weight of oxygen is 32. Similarly, our hydrogen, 2 grams of hydrogen is 1. That means in that fraction, a 2 grams of hydrogen and 32 grams of oxygen are expressed in the same number. You understand, because these are the multiples of the molecular weight. If you express the mass in a different unit, what is that unit? You just scale it by the molecular weight, 1 by m. Multiply with 1 by m. This is known as moles. This unit is known as mole, number of moles, number of moles. This is mass. This is mass in kg. In kg, this is moles, number of moles. And if you do that and substitute this in the equation of state, what you get? N, I am sorry, here you use R bar. That will be no, sorry, no, I am sorry, R. All right, R bar I will use in universal gas constant. Okay. Then if you substitute m is equal to n, then m into R, I take it in a bracket. So this will be the equation of state, modified equation of state, when equation of state is expressed in terms of the number of moles of the substance. That means in equation of state I don't want to use the mass, but I use the mass in terms of the moles. That means divide by molecular weight. So m into R into Nt. Now Avogadro told that all gases at same pressure and temperatures with same number of moles have the same volume. That means if we have different gases whose number of moles are same, that means their masses are proportional to their respective molecular weight, and if they are at same pressure and temperature, they have equal volume, which is not true for mass. That means if we have got different gases or different mass, at same pressure and temperature the volume will not be same. Very simple, density cannot be same. But if the number of moles are same for all gases, at same pressure and temperature they have the same volume. This is because of the same identity of the molecules. That means molecules are alike. Okay. So this is the hypothesis which was given by Avogadro, and because of this we can tell therefore this MR is same for all gases. Clear? Now MR I write as R bar, which is known as universal gas constant. So therefore we see that if we replace m in terms of n, we can write PV is equal to n R bar T. R bar is nothing but molecular weight into R. Well, and which is an universal gas constant. That means which is universally constant for all gases. And this value, since it is universally constant for all gases, should be remembered. I tell you that this value is, we do not go more than 2 places of decimal. It will be enough to remember kilojoule per kg. If I expect something to be remembered, I should not go to an accuracy of 4 places of decimal which have been found out, or theoretically or experimentally it will be sufficient, because its unit will be joule, because this P into V is joule in terms of kilojoule per kg mole. Okay, R bar T. How do you find out kg mole? That is kg by the molecular weight. That is the kg mole. Okay, fine. So this is the universal gas constant. That means if we write again the 2 equations in terms of the specific volume, one is RT, another is PV bar. I will use always these 2 equations. Be careful. One is PV is equal to RT, small v is the specific volume, volume per unit mass. This is volume per unit moles. Just 1 minute. I will listen to all questions. It is volume per unit mole, and R bar is the universal gas constant. So the two equations are same, they are not independent equations. They are expressed in different forms. Here V is the specific volume, here V bar is the molar volume. Okay, please question. Yes.
Sir, unit of R bar is kilojoules per mole Kelvin, not kg.
Kg mole Kelvin. Don't use mole Kelvin. Wrong. Dead wrong. You, from now onwards you write kilojoule per kg mole K. Usually some books write kilomole K, not kilomole, kg mole. Because kg mole has got a meaning that kg by molecular weight is the kg mole. Gram by molecular weight, gram mole. Don't use those nomenclatures given in some books like mole and kilomole. Per kg mole, per gram mole. Okay, all right? Okay? No kilomole business, it is kg mole. Because mole has something to do with kg. Okay? So mole, molecular weight is dimensionless. So kg by molecular weight is kg mole. Okay? All right? You can write kilomole, but I prefer it is kg mole or gram mole. This is my perception. I will better go with this. So this is okay. Now with this, I will. Now therefore, one thing to be again remembered, that for all real gases, limit of P into V bar as P tends to 0 or V bar tends to what? Infinity. Very good. Ratified state becomes equal to R bar by T, only as a limit. Whereas an ideal gas will obey this not as a limiting conditions at all conditions. Okay. Now next is two important corollaries of ideal gases. Now this is the definition of ideal gas. Starts with the equation of state. Now two corollaries. The corollaries are that the specific enthalpy H or total enthalpy you can tell. Now I will deal with specific values only, and specific internal energy are functions of temperature. Now here I tell you one thing, you will appreciate it afterwards, just as an information. Afterwards you will appreciate, when the reaction part is not coming into picture, it is always better with the specific values rather than the molar values. But the molar properties come into picture when reactions are occurring. That means when thermodynamics of reactive systems come into picture, because you will see the significance of dealing with mole in case of reactions and the significance of dealing with mass, the specific properties, when reaction is not there. That is why now I will deal with the specific value. So H and U are functions of temperature only. That probably you know by this time, we have already derived it in course of our other studies, but again I will do that. How do you do? How do you prove that H and U are functions of temperature only? Let us write this expression that dH, if you recollect the very important thermodynamic property relations, which are probably the most important and fundamental property relation, is TdS plus VdP. Very good. Now what is TdS? From the first TdS equation, second TdS equation. From second TdS equation, if you write from second TdS equation, second TdS equation, from second TdS equation, what we know? We know that TdS, if you recollect second TdS equation, I am writing in terms of the specific entropy. So therefore it will be Cp dt minus T into del V. This is the specific value. V Cp, because AC is specific, at constant pressure dP. This is the second TdS equation. This is one of the very important relations, TdS. If we replace this we did while finding out the Joule Kelvin coefficient. It is the similar way, dH is equal to Cp dt plus what is that? V minus T into del V del Tp into dP. Okay. Now then this thing can be written as, this Cp can be written as del H del T at constant pressure D. That means H is a function of T and P. That means as if dH is equal to, if I write H is a function of T and P, I can write del H del T at constant pressure dt plus del H del P at constant temperature dP. This you have already recognize. So this is nothing but del H del P at constant temperature. Now what is this value for ideal gas? If you take the ideal gas equation, PV is equal to RT, and if you use this to find this will be 0, because T del V del T P will be V. If you differentiate del V del T at constant pressure, it is R by P. Del V del T at constant pressure will be R by P, and RT by P means V, V minus V, 0. So therefore this becomes 0, which proves that del H del P at constant temperature equal to 0. So therefore H becomes a function of temperature only. That means if I write dH is Cp dt, therefore from this equation we can write dH is Cp dt, which means this H is a function of temperature only. H cannot become a function of any other quantity, because H can be expressed as P and T, but it is not a function. But you can tell, sir, how do I explicitly prove that H is not a function of volume? That you can do. There are several ways. One of the ways I am telling, it is unnecessary, that PV is equal to RT. So if you keep the temperature fixed, then volume will vary provided there is a variation in pressure. So therefore at constant temperature, enthalpy cannot change with volume if it does not change with pressure. Okay? So therefore enthalpy does not change with volume if it does not change with pressure at constant temperature, because this is the equation of state. So therefore we see enthalpy is a function of temperature only. And we see from here the definition, dH is Cp dt, dH is Cp dt, which means dH dt is equal to Cp. Earlier in first law we have recognized that definition of Cp is del H del T, the specific heat at constant pressure at P. This is valid for all substances. But since H is not a function of pressure, this can be simply written dH dt. Cp is dH dt. Clear? Similarly, we can show that U is also a function of temperature. How to do it? In this case, you have to write du. You start with du. What is this equation? Another fundamental and most important and popular expression is du minus pdv. TdS is du plus pdv. This is a property relationship. Is it first law of thermodynamics? It is first law of thermodynamics. Yes or no?
Yes, sir.
How many of you are telling yes? Du is TdS minus pdv is the first law of thermodynamics? It is not the, no, it is not the first law of thermodynamics. But can it be first law of thermodynamics? Yes, for a reversible process with only displacement work. But this is a property relationship. It may or may not be the first law of thermodynamics. It is first law of thermodynamics under a special situation when the process is reversible and have only displacement work as the work, displacement mode of work as the work transfer. Good. du is TdS minus, because in the Viva these questions will be asked. Nobody will ask you how to deduce the Clausius-Clapeyron equation. Okay. So du is TdS minus VdP. Similar way, if you recall the first TdS equation, what it is? It is Cv dt plus or minus plus T into del P del T V dV. Very good. You write it here, du is equal to Cv dt plus what we can write? T del P del T. T del P del T V dV, V minus P dV. True? Then see what is Cv? Cv is equal to del U del T at constant V. That means du is expressed as functions of T and V. And this is nothing but del U del V at constant T. What is this quantity? If we evaluate this quantity for an ideal gas where PV is equal to RT, this becomes 0. That means U is a function of temperature only. These are very simple things. So therefore, the corollaries, one of the important corollaries of the ideal gas is that U and always du is equal to Cv dt. H and U are functions of temperatures. Now therefore, we come across this thing that for ideal gases, Therefore, we can write du is equal to Cv dt and dH is equal to Cp dt. If you make this is total internal energy, then you make the heat capacity Cv, that both sides you multiply with mass. Similar is the case dH capital H, that is the total enthalpy is the heat capacity Cp into dt. Now, if you integrate this, what you will get? U is equal to integration of Cv dt plus some arbitrary constant. Similarly, H is Cp dt plus some arbitrary, and these constants are neither functions of pressure nor function of volume. This is simply a constant, numerical constant. This is all right. Now, to express this U and H as a function of temperature, we have to integrate this equation, and this is only possible if we know the Cp and Cv explicitly as functions of temperatures. For an ideal gas, we also assume Cp and Cv are constants. They do not become the functions of temperature or any other properties. Sometimes this is known as calorically ideal or calorically perfect gas. Sometimes this is known as calorically ideal or calorically perfect gas. But for ideal gas, when we tell, we always assume that it is a calorically ideal gas until and unless it is told. These are not very rigid things. Sometimes we express that it is an ideal gas, but with a variation of Cp/Cv with temperature. Sometimes when we relax this assumption, make the Cp/Cv varying with temperature, we tell the gas is semi-ideal. So, several terminologies are there. This has to be explicitly mentioned. If nothing is mentioned explicitly, if it is ideal gas given, that means we will assume Cp/Cv are constants. But when Cp and Cv are constants, we tell it that calorically perfect gas. Sometimes perfect gas is a synonymous term for ideal gases. So, if you consider a gas to be calorically perfect or ideal, then Cp/Cv are constants. That means we consider for an ideal gas another assumptions like Pv is equal to RT as the equation of state, that Cp/Cv are constant. Then it becomes simply U is equal to Cvt plus C1, H is equal to Cpt. Now, so long as the difference is considered, I don't care. Del U is equal to Cv delta T. That means I can integrate this. If Cv is constant, I don't care with this constant of integration. That means U2 minus U1 is Cvt2. This thing we have already used. This thing in your with the problems of first law, in the problems of first law, H2 minus H1 is Cpt2 minus. But if I want to ascribe the specific internal energy, a specific enthalpy at a particular state point, I have to know this C1, C2. This C1, C2 are made by a convention for all ideal gases at T is equal to 0, both U is equal to 0, H is equal to 0. So that one can write U is equal to small Cvt and H is equal to small Cpt. So, these equations are valid. Clear? Already we have proved another result, that if Pv is equal to RT is the equation of state, V is the specific volume, then what is the value of Cp minus Cv? R. This already we have proved from thermodynamic relations, Cp and Cv. From two TdS equations, we found out the expression of Cp minus Cv in terms of the derivative of other thermodynamic properties, and utilize this relationship as the equation of state for ideal gas, and we have shown that Cp minus Cv is equal to R. Okay? This is one of the important relations for an ideal gas. Now, I will tell you another important relationship for ideal gas, which is often used in heat transfer studies, that beta that I defined earlier is the volume expansivity or volume expansion coefficient. Expansivity, when you read heat transfer, your teacher will tell that beta for an ideal gas is 1 by T, then you will not be able to tell, then your heat transfer teacher may ask that how you have read thermodynamics. So, it may not be very much related to thermodynamic studies. In free convection studies on heat transfer, we always encounter with this parameter V, volume expansivity is 1 by T for ideal gases. Do not consider that this definition is 1 by T for an ideal gas. How? This I will now prove a simple 2-line proof, primary school level. Beta definition is 1 by V del V del T at constant pressure. Very good. Now you use PV RT and get these things 1 by T. PV is equal to RT, find out this del V del T from here at constant pressure and get this thing. and you will get simply 1 by temperature. Volume expansivity, you see the dimension is temperature, and it exactly becomes 1 by the absolute temperature in case of an ideal gas. Well, another very important relations for PV for a particular process in an isentropic process. Now you know that displacement work W is what? Integral P dV for a given mass, per unit mass, per unit mass P dV. But can you integrate this? To integrate this, you have to know P as a function of volume. So therefore, we have to know the path along which the process has executed this work transfer. That path is specified by the functional relationship of P with volume. That depends upon path to path. So if you know this relationship, I can integrate this, or we can integrate this. So one of these paths is isentropic process. Let us consider that isentropic process. That means S is equal to constant. What is isentropic process? Basically, it is a reversible adiabatic process. Now I write two equations, two important equations. TdS is dH du, what is that? Minus P dV, and TdS is dH minus V dP. For ideal gas, this equation is valid for all processes, property relationship, yes or no? Yes. First one is TdS is du plus, second one negative. Very good, I am very happy. So now you tell me that these two equations are property relations, valid for all systems, valid for all. Very good. Now if I write this as TdS is Cv dt plus P dV, is it valid for all system? It is valid for? Very good. So this is a form of this equation only for ideal gases, and this is also Cp dt minus V dP, it is valid for ideal gases. Now I write these two property relations for ideal gases and consider an isentropic process, that means the left hand side is 0. So then if we divide one by other, that means if we take this side, that means P dV is Cv dt and V dP minus, and V dP is Cp dt, and we divide. Then what we get? We get dP by P plus Cp by Cv into dV by V. I know the result, so without seeing that I am writing, you can also write, it will come like this. And if this is represented as gamma and integrate it, that is ln P plus ln V to the power gamma, gamma ln V means ln V to the power gamma, and in that case constant is also logarithm of some constant ln C, so that P V to the power gamma is P V to the power. This is a very important relationship for an isentropic process. School probably you have done this. P V to the power gamma is constant. So P V to the power gamma is constant is valid for an isentropic process executed by a ideal gas where gamma is constant and equals to Cp by Cv. Gamma is always greater than 1 because Cp is always greater than Cv. That has been already proved. That has been already proved. The next is that now if I equate, this is one important thing that is not very, you can think it trivial, is not very important, but once you do it, I feel that it is better that you remember this formula, otherwise there will be no problem in deriving this, that if we have to evaluate this integral from a point 1 state point to 2, and if you have got a relationship of this, sometimes for all other processes, reversible processes, it is possible to express the PV relationship like this. So all other reversible processes, it is possible to express the relationship as this, PV to the power n is equal to constant, where n has got any value. When n is equal to gamma, the process is isentropic. Okay? When n is equal to 1, the process is isothermal. Very good. PV isothermal for an ideal gas, all for ideal gas, and n is equal to 0, isobaric. So you see that for any value of n which may not be equal to 1 gamma 0, it represents a reversible process which may not be isentropic, may not be constant pressure, may not be constant temperature, but it is a reversible process. So if any reversible process, the path of the process is prescribed by a functional relationship of PV in the form of a power law, that PV to the power n is constant, then one can integrate this, let this is equal to constant C, then one can relate it C, just school level integration dV by V to the power n. So if you do this, then what you will get? V to the power C 1 minus n. So V to the power 1 minus n from 1 to 2. So 2 V2 1 minus n and C is P2 V2 to the power n. So this becomes 1 minus n P2 V2 minus P1 V1. Because V2 1 to the power 1 minus n minus V1, this bracket after this it will be, after putting the limit, so this will be like this. So when it will be multiplied with C, which is P2 V2 to the power n, here that will P2 V2. When you will multiply with that, we will use P1 V1. So this is a very important expression. So if n is equal to gamma, this will be 1 minus gamma. So depending upon the value of the index and the corresponding values of PVs at initial and final state, the sign of W will be determined, so that you can find out whether the work is coming out or work is going into the system. So next is what? PdV for a polytropic process. Then we come to the entropy change of an ideal gas. Entropy change of an ideal gas. How do you calculate the entropy change of an ideal gas? Entropy change. Now you see the entropy change of an ideal gas is very simple. Again we start from the same equation, that TdS is equal to CV dt plus what? PdV. TdS is Cp dt minus VdP. Now for the 2 points, pressure, volume, temperature, all these things may not be given. Pressure, we may know pressure temperatures, we may know volume temperatures, or we know everything. So you can use any pair. So if you use the temperature and volume, you use this. What you do? ds is Cv dt by T. Now P by T, what is P by T? PV is equal to RT. So P by T is R by V. dV by V. So therefore S2 minus S1 is Cv ln T2 by T1 plus R ln V2 by V1. Any question? All right. Very simple, school level. So similarly, if you integrate the second one, you get Cp ln T2 by T1. What I will get? V by T minus R ln P2 by P1. So the change in entropy between these two states given by T and V and P and T we can use, and P and V we can make from these two equations, we can find out the relationship between P and V. Okay? So this way we can find out the expressions for what? For entropy change of an ideal gas. So therefore we have to remember for ideal gas all those corollaries while solving problems. So after this I will start the real gas. What is a real gas? But well, the few real gases and how we can express the equation of state for a real gas. But I think today the time is limited, much time is not there. So I will start the expressions for real gas, how it deviates from the ideal gas, and how you can express the equation of state of a real gas, compressibility factor and all these things I will discuss in the next class. But before that, you ask me any questions you do have. Today is extremely simple what I have taught, but regarding, just a minute, till 5 minutes we can spare if you feel so, that we can discuss anything about the change of phase diagram and all. Any question? No question?